let's start with work.
Applied and the displacement is in the direction.
Work.
Dot product of force and displacement.
Work or work done. Work or work done is scalar product of what? Force and displacement vector. Okay, so if I have any block here and I give you a force, no, now I'm not going to give the force like this. Let me give it a force at certain angle theta to the what? Through the horizontal. So this is theta. The box will move to certain displacement after some time. Means if this is my origin, this distance is x1 and from here this is x2, that means this displacement is how much? x2 minus x1. We denote this by s, displacement s. So that means I can draw the displacement vector like this. Then the work done will be defined as what? Scalar product of force and displacement vector. That means F vector dot S vector, which you can write as Fs cos of theta. What is theta? But theta equals to angle between what and what? Force and displacement vector. I'm just writing force and S vector. Okay?
Yes.
Now, based on theta, case 1, theta equals to, let's say 0. What do you think at that time? So W would be equals to FD cos 0 degree. That gives me FD. That means work done is maximum. It's positive and maximum. W equals to W max and that gives me FT. Fine?
Yes.
Case example. What is the example? Example will be, I take this box. It can be a box, it can be whatever. You are pushing it directly in the same direction of the displacement. So this is F vector and this is also your displacement vector S. So in this case both are in the same direction, so work done will be maximum. Correct? Case 2.
Yes.
Now case 2, what do you think will be the case 2 then? So for case 2, how we can write? So for case 2,
90 degrees.
so case, let's say theta equals to 90 degree. Then
work done is 0.
work done would be equals to FD cos 90 degree. So that is 0. So we call this as what? 0 work done.
Yes.
Now I will give you an example. The 0 work done example, there are so many of them. Let me give an example of 0 work done. It's a very, very important concept. Let me give an example of 0 work done. There are so many of them. So first 0 work done I will give you. You must have seen porters. When a porter, example of 0 work done. Example of 0 work done. You must have seen porters, means the person who carry load or the person who come at your household to deliver cylinder, gas cylinder. Where do they carry the cylinder, which is very heavy, which is 28 kg gross weight?
On their head.
Why? Why? So if this is a person, I am showing you with the stick, okay, stick diagram. This is the person. If they carry a load like this at the head and they are moving this way, right? The weight of the body as well as the man is which way? Mg downward. And this is the force. What is the angle between them? 90. So work done is 0. So whenever you are carrying heavy load, you should carry it on your head. Okay? Better is head. If you cannot carry on head, you definitely carry it on your shoulder. But remember, you will need lots of strength, lots of potential, lots of force to take it to your height, because you're going to impart potential, you're going to increase potential energy of the mass, correct? But once you take it to your head and place it there, it becomes very easy. Understand? So therefore, this is another example, very important. So this is the first example. Another example would be, look at this case. You have, this is the earth, this is the moon, which is spinning in a, let's say, in a circular orbit around the earth. Not only the earth, or let's say like this, this is a stone which is tied to a string, and this is a person who is rotating it. You can see any motion like that. Okay, it can be moon around the earth, whatever be the motion. This is a particle which is spinning about this. So this is definitely his velocity vector, linear velocity vector. This is the radius r, right? This is the radius r. What we can write? What you can write? Can you write? For, we know what work done will be what? Work done is written as force into displacement, right? Correct? Or per second it would be how much? Per second. It can be written as F dot V, right? Is it or not? Percent, work done per second, which is what? Power, right? So the velocity vector is directed this side. Come on, if not, displacement is also directed perpendicularly. For example, the particle has moved from here to here. This is V1, this is V2. It has moved from here to here in time. The displacement is this, which is again perpendicular only. Correct? Now F dot V, or work done per second, would be F dot V. You can write this as what? You will have to write this as FV cos 90, which is again what? 0. Right? So what is another example? A body tied to, so work done by the centripetal force, on rotating about a center is what? 0. Another example. Why I am giving you this example? All these examples you will be coming across throughout 11 and 12. Case 3 will be, look at the pendulum. This is toward the vibration chapter. This pendulum, if you give a very small, as long as you keep the oscillations very small, you oscillate it. So what do you think will be again the force? This is the displacement. For small displacement, this is almost a straight line, right? And you have given the force which way? The force or the tension? Tension is which side? This is the tension T. This is the displacement. Again you see angle 90. So what you can say? What can you say? Work done by tension in a string of a simple pendulum is 0. Okay? So these are the 3 cases we have learned. 1, 2, 3. Now the third case of work done. What is it? So can you see here? So this is what? Work done equals 0. So it's a what? Positive work done. I will highlight this concept of positive work done and negative work done more properly, but you try to understand this, what is positive work done and what is negative work done. Let us see now the third case. Case 3 means case 3 of which one? The first case, okay? So when theta equals to greater than 90, I will write like this. When theta is greater than 90 and less than equals to 180, then what do you see? Then work done would be F vector dot D vector equal to FD cos 180 degree. What do I get? W equals to minus FD. Here you can see work done is negative. Now what do you understand by negative work done and what do you understand by positive work done? Energy can also be positive, energy can also be negative. Okay, here this one is positive work done. W equals to positive. And in this case W equals to negative. Right?
Yes, sir.
Can you give me an example of negative work done? Can you give me a very simple example? Let me throw a ball. Upward. This is what force? Gravitational force. Okay? Your direction of displacement is which side?
Upwards.
Direction of displacement. Then work done will be what? Fg dot S, which is minus FGS cos 180. Sorry, here it is plus, so W would be minus FGS. Isn't the work done negative? So work done by what? Work done by gravity. Gravitational force is negative when the object is going up, but when it's falling down, then
Percentage should be positive.
wait a minute. Let us understand this concept in another way. Look at this 2-bar magnet. North, south. This is another north. This is south. Okay? You are pushing. Here two forces are present. It's a very important concept, as we're going to deal it towards the end. There's a two force I can see. One is the force of magnetism, magnetic force, and another is the applied force. Right? If you are bringing this, let's say you are pushing it very hard, you are bringing the North Pole towards the North Pole. Will it be easy for you to bring?
No, sir.
So your displacement is happening which side? Displacement S is here, right? So this is the x2. This is, let's say you brought from here to here. Okay? This is x1. The displacement is how much? x1 minus x2. Sorry, this is x1. This is x2. Keeping this as the origin. Keeping this object as the origin. Tell me, is the work done positive or negative? Positive or negative? If the force is the external force, not the magnetic force. Force and displacement are in which direction?
So opposite to each other.
How can you say? The applied force and the displacement are in the same direction.
Okay.
So what is this? Work done is, so work done by the applied force is positive, but
Yes, sir.
work done by the magnetic force is negative,
Yes.
right? Now you see, when you are bringing the north pole forcefully towards the another north pole, can I say the potential energy of the system is increasing and it is positive? As it is increasing, so it's positive. How can you say potential energy is increasing? Because as soon as you release the applied force, what will happen? The north pole, the second bar magnet, will fly away. Considering the first bar magnet is fixed, the second one will fly away or not, because there will be repulsion between them. Correct? Is it? Is it?
Yes, sir.
So that means potential energy is increasing. Now if you do the opposite, if you take away, you do not need to do much work. Potential energy of the system is automatically decreasing. The energy is decreasing. Remember this concept. We'll come back to this once again in very near future. So now this is all about work done. Now one more thing. Graph. What do you think will be the graph of? So what is the cos theta curve? Curve of cos theta is, do you know the curve of cos theta?
Yes, sir.
Hmm?
Yes, sir.
So the curve of cos theta is,
Yes.
right? This is 0, correct? Then at 90 degree it is 0. Again its value is -1. So this is 1. Sorry, this is 1. This is -1 at what? At 180, and again so on. So this is, so based on this, what can we say? Whenever the angle between the angle between force and displacement will be between 0 to 90, I'm going to get a positive work done. And when I'm going to get it from 90 to 180, it will be what again? Negative, correct? Or 180 to how much? So on, like that, so on. Done?
Yes.
So you understand the zero work done. Now how will you do solve problems? Okay, before that let me come to unit of work done. Unit of work. What is unit of work?
Joule.
Joule you already know. SI unit of work is Joule. Other unit of work?
Meter.
Other unit of work is electron volt, EV. Its dimension is, one more thing, dimension of what, W, what do you think it is? Force into displacement, which will give me, dimension of work done will be ml t to the power minus 2 into L, which gives me m L square t to the power minus 2. What? Same as energy. Therefore, other unit of work is electron volt, which is also the unit of energy. Okay, Joule is the unit of energy. Similarly, So 1 eV equals to how much? 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. Example, if I ask you convert 100 joule into EV, how will you do it? Sorry, into EV. What will be the answer? 100 joule. 1 joule is this much. 1 joule must be equals to 1 by 1.6 into 10 to the power minus 19. Now what is this number? 1.6 into 10 to the power minus 19. It is the charge on an electron. Okay, charge on an electron, not the plus or minus nature. I am talking about the charge, magnitude of charge on the electron. So this much is the EV. So 100 joule will be how much? 100 joule will be 100 divided by 1.6 into 10 to the power minus 19. So that gives me around 19. It gives me how much? 1 divided by, yeah, it's a large. Let's see, I'll show you what is this. So it gives me 10 by 16 into 10 to the power 19 minus 2, that is 17 EV. Okay, so 10 divided by 16, roughly how much? 0.16 5 6 9, I think 0.6 roughly. 0.6 into 10 to the power 17 electron volt. Hence, you can see how large is this number. How large is this number? Therefore, we have other unit, large unit of EV. Other large unit of EV will be giga, mega. Okay, giga, mega, giga, tera, all this. So giga will be 10 to the power 6, mega will be 10 to the power 9, tera would be 10 to the power 12, and so on. We express it like this. So then this is the unit of work. Done?
Yes, sir.
So two things to note from here. Perhaps you have understood the nature of work done, when the work done is positive, when the work done is negative, how to identify them. Okay, clear?
Yes.
Okay, now let me clean it.
Yes.
Yes, sir.
Do this problem. A body is pushed over a surface, the mass of the body is 5 kg and it is displaced through a distance of 10 meter by a force of 50 Newton. The coefficient of friction between the surface and the body is 0.5. Find number 1 work done by the external force, number 2 work done by the frictional force. Try.
So by external forces it is 500 joules.
Okay. Number 2.
So minus 250 joules.
Minus 500 joule. Minus 500 joule. Why?
Sure, but coefficient is 0.5, so how it is minus 500?
Wait. That is the trick I played with you. Draw the free body diagram to understand. This is the F. This is the friction. Is the body, did I say the body is accelerating? The body is under constant velocity. Nowhere it has been mentioned that body is accelerating. So that means what? F minus F equals to what? Right? Is it or not? And what is the angle between the displacement? It is taking place which side? Marna, from next day, no, please put your phone on silent, huh?
Yes.
So then, plus FD cos 180. So minus FD, which is what? They are equal only. Minus 500. We will use this. When to use this, you will understand.
So, but if there is no acceleration, should the force only not be 0?
No, the body is under uniform motion. There the friction is present. Friction is not 0. Friction is there. Try to understand the situation there. Friction is not 0. Friction is present. Okay? Try this question. May I clean it?
Yes.
A car comes to rest in 5 meter when brakes are applied. The force on the car by the road is 100 Newton. How much work does the road do on the car? And number 2, how much work does the car do on the road?
So the car does 500 joules of work.
How much?
So 500 joules.
Okay. So the second question is important. How much work does the car do on the road? What is the answer to the first one? So this is the car. The brakes have been applied. The car stopped by distance of 5 meters. So work done would be, the frictional force is this way, displacement is this side, so they are in opposite direction. That means work done must be equal to F S cos 180. So that gives me how much? Minus 5 into 100, 500 joule. This is the first one. Second one, this is non-intuitive. Now let me tell you something. We are going into some chapters, we are gradually getting into some chapters in which your answers cannot be intuitive. You cannot have intentions. You cannot give these answers from your intuitions. Your intuition will say something, but maths will say different. Look at this. For no, not for. The road do not make any displacement. Does it make any displacement?
No.
So what do you think the work done then? How much work done by the car on the road? 0. So work done by the car on the road is 0. Clear?
So can you explain the first part once again?
Which one?
So first part.
How much work done by the road?
On the car.
Yeah, definitely road is giving a friction. He is applying the... See, a car engine do not provide anything. It just is the internal force. Okay? It provides you, I will not say anything. It provides, its purpose is to just rotate the wheel. If the friction between the car wheel and the road surface is 0, means they are very smooth, they are very polished, do you think the car will be moving forward? The wheels will keep spinning only. Wheels will keep spinning, it will never move forward. Right? In system of particles, that is the toughest chapter, system of particles. I will discuss rolling motion also much elaborately. So, the friction in this case is just sufficient enough for the wheels to spin, to rotate, not to skid, not to slip, not to drag. Okay? Exactly sufficient enough. They are not max. If they are max, the car is not moving. Okay?
Yes.
So in that situation, the work done is negative, because the frictional force and the displacement, they are in the opposite direction. Right?
Yes.
It may happen The wheels has stopped because of the brake. Okay, but the car is still sliding.
Yes.
That's why in today we have a technology called ABS. Google it to know about it. All new vehicles must have this ABS technology. What is ABS technology? It balances the brake in such a way that during curve or during very hard brake, the wheels will not come to complete rest. You will not slip. You will not skid. The wheels will rotate in a balanced way. Got it?
Yes.
So this situation we have studied now. Try this question. It is another famous situation. This is a truck. There is a box which is kept over the truck. Very common situation. The weight of this block is 100 kg. And the truck is moving with an acceleration of 2 meter per second square.
Yes.
There is no relative motion between the block or box and the truck. This point is very important to mention. Means it is not skidding, not slipping. Right? What is the work done? What is the work? Now this question I can give you in many ways. Let's say the car suddenly comes to a rest. The truck suddenly comes to a rest. Right?
Yes.
That can be done, but let us do the another one. What is the work done by the frictional force? By the frictional force on the block as the truck is displaced by 2 meter with respect to ground. Can you? Give me the answer.
So 100 kg is the weight of the box.
Yeah. What do you think?
The speed is 2 meter per second square constant.
Hmm?
So the speed of the truck is 2 meter per second square constant.
Can you do something like this? So what is the force? I said, look at this. This point is very important here. The hint is here only. So can I say again the free body diagram? This is F. This is
Zero work done.
friction. No. F will be what? Mass into acceleration. Mass is 100 into 2. That gives me
But
200.
you told 2 is the velocity.
2 meter per second square I have written, na? So friction would be, what do you think the work done will be now? Work done would be F into D into cos of 180. So minus 200, displacement is how much? 2
2 meters.
minus 400 meters. So all your intuitions, I am going to break it. Don't worry with the numericals. All what you think naturally, I think this would be like that. All those things I'll break it. Don't worry, gradually.